Hi everyone, welcome to this new webinar on AWS Graviton2 processor. So today we have a special guest, Lise Fong Jones from honeycomb.io, and she will be, after my short introduction, she will be speaking about their journey to adopt Graviton2 based instances, and she will show you what they've done and how they've benefited from that new processor. Before that, let's start with a quick introduction on what the Graviton2 processor is and how you can benefit from it for your workload on AWS. So the Graviton processor is a custom AWS piece of silicon based on the 64-bit Neoverse cores. So that's the ARM architecture that we use on a server processor. And it's targeted specifically for cloud-native workloads. AWS has started a brand new range of in-house design processors to be able to rapidly innovate, build, and iterate based on customer feedback, and to make those processors specifically targeted to what our customers are doing. Compared to our first generation of Graviton processors that we released in 2018 and that were powering the A1 instances, the Graviton2 processor is a totally different beast. It has 7 times overall the performance of the first generation of the Graviton processor. It now has 4 times the number of cores. We have up to 64 cores on the Graviton2 processor. It has a way faster memory and twice the amount of cache. In terms of manufacturing technology, we moved from a 16 nanometer technology to a 7 nanometer. And we managed to put 30 billion transistors on that massive chip. Today, we have 6 different instance types using the Graviton2 processor. We have our classical M, C, and R families. So they are called, for the Graviton processor, M6G, C6G, and R6G. And they are the equivalent of our C5, M5, and R5 Intel-based instances. However, they are offering a way better price-performance ratio, up to 40% better price performance compared to those Intel-based instances. We also offer a burstable instance based on the Graviton2 processor. So that's the T4G, and that's a good vehicle to replace your existing T3 or T3A instances with a better price performance ratio. We also released the C6GN, which is exactly the same as the C6G, but with a more important network bandwidth. You have up to 100 gigabits of network bandwidth on the C6GN, which makes it a really good vehicle for any super network demanding workload, like anything that would be doing packet processing or tightly coupled HPC workloads, given that that one also support our EFA interconnect. And we have more recently released the X2GD. The X2GD is the latest one in the Graviton2 family. That's an instance with up to 1 terabyte of memory. And that's the one with the cheapest dollar to memory ratio. So if you really need a lot of memory, the X2GD is a good instance type. They are all available right now, and for M6G, C6G, and R6G, there are variants with local SSDs that you can utilize. And for most of those instances, except the T4G and the C6GN, there are also metal version of those instances. So instances where we have removed the virtualization layer so that you can directly access to the processor and do things like either testing or experimenting with your own virtualization layer, or accessing the lower level performance scanner to do sophisticated performance analysis. All the Graviton2 based instances are based on our Nitro ecosystem. So they all support the Graviton2 processor. They use the Nitro security chip that is protecting all the component on the motherboard from being tampered by any external attacker. They use the Nitro cards that are exposing the EBS devices, our network adapters, and that are providing monitoring and security features for the Graviton2 based instances. And they all use the Nitro hypervisor, which is our new generation lightweight hypervisor that is providing bare metal-like performance to virtualized instances. Today, those instances offered the lowest possible cost in our instance families. They are the highest performance in their instance families, and they're 20% lower cost than the same sizes for comparable instances. So for example, if you compare a M6G 4XL, that's going to be 20% cheaper than an M5 4XL. And on top of that, they tend to perform a lot faster. So we tend to say up to 40% better from a price performance. And of course, there are two components to that 40% better price performance. On one side, there's the 20% lower cost, and there's the performance that you might get from those instances for your specific workload. And here, we do see, on average, something around 20%, and in some cases, you will get a lot more than that. In terms of managed services, we use the Graviton2 based instances not only for our EC2 instances, but we've also started to deploy them for some of our managed services. The first one was Elasticsearch. So you can now use Graviton2 based instances for your Elasticsearch setup, and they offer better performance and lower cost. And we were confident enough with the Graviton2 based instances for Elasticsearch that we've even made them the default. So when you install an Elasticsearch setup for the first time, if you choose the default instance type, that's going to be a Graviton2 based one. We've also introduced support for Amazon EMR, so you can run your big data workloads on Graviton2 based instances. It is now also supported for Amazon RDS for different flavors, including MySQL, Postgres, and MariaDB. And we've also added support for Amazon Aurora. For most of those services, there's a minimum version that you need to be using to benefit from the Graviton2 based instances. The last addition to our families of managed services that support the Graviton2 based instances is Elasticsearch that we released early May. So you can now benefit from the M6G, C6G, R6G, and R6GD instances when using Elasticsearch on AWS. And you will get a better performance at a lower cost. So there's really no reason not to use them. In terms of operating system support, the Graviton2 based instances are supported by all the major Linux distributions. Of course, you can use and benefit from Amazon Linux too, and we've taken all the care we could to ensure that you would get the best performance out of them. Red Hat is also an excellent alternative. You just have to be sure that you can use a version that would be at least Red Hat 8.2 to get the full support for the Graviton2 processors. SUSE 15 SP2 is also an alternative. And finally, Ubuntu has support for multiple versions, including the 1804 and the 2004. if you rely on open source community-based operating systems, there's support for most of them also. So you can use CentOS, you can use Debian, and you can even use FreeBSD or NetBSD, which shows how easy it is actually to port a new operating system to Graviton2 based instances. If your workload is based on containers, there's a good news. All the container runtimes are supported on Graviton2 based instances. So that's of course true for Docker, but that's also true for Kubernetes if you're installing it by yourself. Our two managed services doing container orchestration do support the Graviton2 based instances. So you have the opportunity to use either ECS or EKS and benefit from those instances. And in terms of registry, there's an interesting feature that you need to be aware of. That's the multi-architecture feature that you would find on most of the registries. So that's true for Docker Hub, but that's also true for our own Amazon Elastic Container Registry. And that feature would allow you to store two container images, one for the ARM64 architecture and another one for the X86 architecture, and push them under the same tag to the container registry, so that at runtime, your system would pull the right version from the container registry, depending on the microarchitecture of the execution host. For information, there's also support for the Graviton2 based instances in Bottle Rocket, which is the Amazon version of a container OS, so dedicated to running container workloads through orchestrators. And we also have support for Firecracker, which is our open source implementation of a micro VM. In terms of tooling and software, the support today for most of the toolkits and SDKs that are coming from AWS. So for example, Amazon CloudWatch or AWS Code Deploy, the many different agents that we are releasing, they all support Graviton2 based instances. A special mention for Amazon Corretto, which is our long-term supported version of OpenGDK. With Amazon Corretto, we do specific optimization for the Graviton2 based instances, and we ensure that Amazon Corretto is compiled the right way for the Graviton2 based instances. So if you are running Java-based workload on top of Graviton instances, we really recommend giving it a try. We've seen customers getting 20% better performance with Amazon Corretto on Graviton2 based instances compared to the upstream version of OpenGDK. All the patches that we are doing are pushed to OpenGDK, so most of the difference actually comes from the way we are compiling it. In terms of ISVs and partner support, the Graviton2 based instances now have support from many different commercial softwares. On the database front, we have support from all the major open source databases, including Cassandra, KeyDB, MariaDB, ScyllaDB. In terms of configuration and monitoring software, same thing. We have support from many different vendors. Datadog was among the ones that were early adopters. Honeycomb, Lise is going to talk more about that today. They've done an amazing job at both supporting the Graviton2 based instances, but also using them to offer their services. On the security front, CrowdStrike has made available its security agent. We have support from Qualys and Rapid7. And finally, most of the CI/CD tools are now available for Graviton2 based instances, so they allow you to build and deploy your software. Now let's talk a little bit about what it means and what are the potential good use cases to migrate to Graviton2 based instances. So the first workload I would recommend would be anything that would be using one of our managed services like RDS or Elasticache or even Elasticsearch. They tend to be super easy. You just need to upgrade to one of the versions that are supported by those managed services and ensure that your application can run with that one, and you can benefit from better performance and lower costs. Another super easy one is EMR. It typically just works. You just need to pay attention to potential GNI modules that you might embed so that you would ensure that they do support the ARM 64 architecture, or if you are installing Python native modules on top of the existing toolkits, those need to be compiled specifically for the ARM 64 architecture, but it tends to work pretty in a pretty simple way. Still quite easy. Any workload that would be running on Linux with high-level languages. You just need to pick up an ARM 64 AMI, install your application on top of it, and you should be good to go, because the architecture part of the support is done at the interpreter or the JVM level. Bonus, if you're using containers, that's going to make it even easier. You just need to generate an ARM 64 version of the container, and you should be good to go. Slightly more involved would be the Linux-based workload using lower-level languages, things like C, C++, Rust, Go. Same thing, you need to pick up an ARM 64 AMI, and here you will have to recompile your application. The good news, though, is that there's support from all the major compilers for the different languages, be it GCC or the Rust compiler or the Go compiler. And usually, unless you're using some really specific platform features like intrinsics or handwritten assembly, in which case you would have to port them. But usually for most of the application, that's going to be a straightforward recompilation. Another type of workload that people are sometimes forgetting about would be the Microsoft Windows .NET workload. We have a wonderful framework helping you to migrate from Microsoft Windows /.NET to Linux /.NET Core. And once you've done that migration, yet another step is to move that to Graviton2 based instances. .NET Core is performing really well on Graviton2 based instances. So that's yet another step that you can do to get better performance and save on the cost. For Microsoft Windows purely based workload, I'm sorry, we don't have yet support from Microsoft Windows on those instances. Thanks a lot for listening to my presentation. I'm now going to give the mic to Liz, and she will be speaking about their journey, the Honeycomb journey to adopt Graviton2 based instances. The floor is yours, Liz.
Thank you, Arthur, for the intro. So today I wanted to share our real-world case study about how we saved 40% on our highest volume service, as well as across a variety of our other workloads. So at Honeycomb, we're big fans of Graviton2. So just to introduce myself really quickly, my name is Liz Fong-Jones, and I'm the Principal Developer Advocate at Honeycomb, and I help bring Honeycomb's technologies to the world, as well as bring innovative new technologies such as Graviton2 to Honeycomb. So I first heard about Graviton2 in December of 2019, where I was watching the AWS reInvent stream and heard about Graviton2 and its price benefits, as well as its performance and environmental impact benefits. Specifically, hearing that there was a new kind of processor that we could leverage for our workload seems like something that we ought to try in order to improve the performance and price of Honeycomb. So, as Arthur said earlier, the Graviton2 processor is a lot cheaper and is a lot faster. So let's talk into some of the details of why that is in order to understand what workloads it's good for and how we can best leverage it. So if you think a little bit about the processor architecture differences between X86 and ARM, X86 has a complex instruction set. It consists of a large number of very complex instructions that must be decoded and transformed into lower-level processor operations. Whereas the ARM processor is a reduced instruction set, and therefore it can devote more of its processor die just to doing compute, and it doesn't have to worry about doing that high amount of instruction decoding and transformation. Additionally, the current set of processor architecture designs from Intel are primarily on the 10 nanometer process, and we know that the smaller that the process node gets, the more power efficient the processor is. So with a 7 nanometer process node, the Graviton2 processor can have a higher transistor density and can consume less power. So that leads nicely into why, core for core, the ARM processors are not just cheaper, but faster. With x86, you have the simultaneous multi-threading technology, which results in 2 virtual CPUs, each having an independent decode unit, but sharing a single execution unit that they interleave. Whereas on ARM, there is no simultaneous multi-threading. One virtual CPU is one decode in execution unit. So there's no sharing of those execution units between threads running on different vCPUs. Now, of course, Amazon doesn't share a single core between 2 different tenants on x86. So you don't have to worry about security risks. But it does mean that your workload is contending with itself every single time if you're trying to perform 2 operations at the same time. So the fact that when you buy 2 ARM vCPUs, you get 2 independent execution units means that you are not contending with your own workload, and therefore there's less tail latency and less performance variability, which means that you can push your instances hotter. And you can run them at 70%, 80%, or even 90% CPU saturation, rather than needing to hold the line at 50 to 60% as you would on x86 in order to limit the variability and amount of tail latency. We'll talk a little bit about how this matters and how this impacts which workloads we might pick to move on to ARM and how we might benefit compared to x86. So a year later, after the 2019 reInvent keynote, it turns out that some of the work that I did to bring Graviton2 to Honeycomb wound up being featured on the reInvent stage, where Andy Jassy featured our story. And in this story, we outlined how after a month of prototyping, we were able to publish a preliminary blog post with our findings, saying that we were able to run 30% fewer instances and that each instance costs 10% less. And this was migrating from C5 to M6G. However, we have since migrated this workload even further onto C6G, which was not available in the first month of Graviton2. But, let's back up a second, right? Like, every architectural change has a risk associated with it. And yes, I am going to insert a pun here, right? Like, is it worth the risk? Both in terms of, is it worth switching to the reduced instruction set? And also, is it worth the infrastructure churn to Honeycomb? So let's back up a little bit and look at the business problem that we're trying to solve. So Honeycomb is a data storage engine and analytics tool that enables our customers to understand what's happening inside of their production applications. So we ingest telemetry from our customers, who are very often running on AWS themselves. And we store that telemetry about what functions were called within the application of our customers, which remote procedure calls were issued, and so on and so forth. And we ingest that data in real time. We index on every single column, no matter what the cardinality is. And we enable near real-time querying on every piece of ingested data, as well as enabling historical data querying across months of data. So as a result, we have to think about this workload as a high-performance data workload. where we need to be able to do bulk ingest at very high throughput and at very low latency. So in order to run a reliable system that meets our customers' expectations, we have to keep service level objectives. Service level objectives are a concept from the world of site reliability engineering. They're a mechanism for us to have a common language between engineers and business stakeholders to agree what is the level of performance and reliability that our customers expect, and how can we make sure that we achieve that. So we measure a few key user workflows for Honeycomb. For instance, we expect that the Honeycomb homepage will load quickly so that users can quickly get an at-a-glance view of their data. We expect that when a customer runs a query that they can generally get results back within about 10 seconds at worst. And finally, and most importantly, we only get one chance to ingest data from our customers. If we drop an event, we do not get a retry. So we aim to ingest 99.99% of data that's coming into Honeycomb, and to ingest it within a matter of milliseconds so that our customer applications do not have excessive buffering. So when you look at this means that we are only allowed approximately 4 minutes of degraded or slow time if it were impacting 100% of our user queries. And as user traffic volume rose, we had to run more and more C5 instances in order to achieve our performance targets. This was not necessarily a great thing for the health of our business financially. And we also had to take proactive actions. If the error budget looked like it was going to be in danger, we had to do things like restore service by rolling back a bad release, scaling up our instances if the auto scaling didn't work correctly, or so on and so forth, right? And certainly it's a lot better than having to respond to a potential cause alert, like, oh, the CPU is too high, right? Like, we'd rather get alerts on real actionable things impacting our customers, but it's a lot better if we can proactively manage our service in order to stay well clear of violating our SLO. So we need to think about both our amount of reliability and our amount of cost. Because if we are in a place of having really good reliability, we can take a few risks and experiment more. And that was our situation in January of 2020. We're in a time of peak reliability. We are overachieving our 99.99% reliability target, so we knew we had a little bit of room for leeway in terms of experimentation. Additionally, as I said, in 2020, we were thinking about things like, how do we manage our infrastructure costs, knowing that we were at the time a Series A startup, and infrastructure was our number 2 expense, right? Our AWS bill was our number 2 expense after the salaries of our engineers and of our salespeople. So our infrastructure costs, and like our cost in terms of number of engineers, the infrastructure cost scales with the amount of traffic we receive. If we double our traffic, if we don't do anything to optimize our infrastructure costs, we're going to double the cost of our Amazon bill. This isn't great, right? So as a software as a service business, we need to think about minimizing the cost of goods sold in order to make our business as healthy and sustainable for the long term as possible. So that kind of combination of factors is why we considered Graviton2 in January of 2020. That we had high reliability, a growing amount of costs that we needed to cut, and a little bit of engineer experimentation time available. So given these constraints, we wanted to do an experiment that would let us validate that we could adopt Graviton2 with as little pain as possible and to demonstrate as large of a cost savings as possible. So let's talk first about environments. One of the things that we had to deal with first was thinking about which of our 3 environments do we deploy Graviton2 into. So in production, our customers observe their own data using the Honeycomb telemetry and analysis suite. This is not a great place to start an experiment because as much as we do advocate testing your code in production, we also advocate testing it first in a pre-production environment, right? Just because you're testing in production does not mean that you're not also validating before it reaches production. Additionally, during the early proof of concept for AWS Graviton2, the terms of service said we couldn't run a production workload, that it was for analysis purposes only. Okay, so not production then. But dog food. We have a second copy of Honeycomb that observes the production copy of Honeycomb. It's how we debug Honeycomb itself. So it runs the same exact code, but it's looking at the telemetry coming out of a production environment and ingesting it for the analysis of Honeycomb engineers. And in it, we can do things like look at the adoption of features, for instance, like service level objectives, which are a part of the Honeycomb product suite. So we can look at things like that inside of the dog food environment. But we also need visibility into the dog food environment itself. So we have a kibble environment that observes dog food that we can use to troubleshoot and debug if we do something that breaks dog food. So you might say, okay, why not push to kibble, right? Like kibble is the least important of all of these environments. It turns out nothing observes kibble itself, right? That the set of turtles all the way down has to stop somewhere. So as it turns out, we decided that we were going to observe the dog food environment using kibble, and we were going to experiment with Graviton2 and dog food and analyze those results using kibble. That way we had something we knew we could trust that we could use to analyze the results of our experiment. So now we decided that we were going to do an experiment in dog food. But which service should we migrate? Well, we've got, basically almost a dozen microservices, right? Or, we don't really think of them as microservices, right? They're very horizontally scalable macroservices. And we've got, a dozen of them. So the key thing that we looked at was, can we do something that is high volume, right? That's not, a tiny service that receives no traffic, right? The goal is saving money. And can we do something that is going to minimize the threat should something go wrong? So the key workflow that we follow when people use Honeycomb is data comes in through api.honeycomb.io, flows through a stateless ingest worker called Shepherd, gets written to Kafka, which stores the data transiently. And then that data is indexed by the retriever indexing service and written to S3. And then finally, when customers issue a query, it comes in through our web front end and issues a request against the retriever data storage engine. We also have several MySQL databases, but at the time there wasn't MySQL as a managed service like RDS for Graviton2, and we didn't see a reason to go backwards from RDS to non-RDS. Okay, so out of those, let's have a look at what the options are. Poodle is a tiny, tiny service that doesn't really consume that much in the way of resources. Sure, it would be nice to do as a proof of concept, but we're not going to see any real money savings here. Retriever, right? Like Retriever is this huge, huge data storage engine. But the problem is it needs a lot of local solid state drive on NVMe. And the initial pilot of M6G did not provide on-instance storage, so that wasn't going to be a good fit for us. Kafka, same deal, right? Like it's a stateful storage, it requires a lot of on-instance storage. And it also, if it breaks, it's catastrophic, right? That interrupts the entire flow of data and is difficult to recover from. So that leaves for us Shepherd, which is a stateless service, right? So therefore, it is something where if there's a problem, we can roll it back. And secondly, that it's very, very high volume because every bit of telemetry coming through api.honeycomb.io goes through Shepherd. So therefore, we picked Shepherd to work with as the service that we were going to migrate for the first time. Additionally, Shepherd has this property that it's very easy to measure the performance because it's a very predictable workload. And like Retriever, whose traffic depends upon our customers doing a lot of queries or not, at all times of day, Shepherd is retrieving traffic, and we're trying to scale it based off of the amount of CPU utilization. And we have a target throughput that we're trying to maintain. And as I said earlier, right, like we can't delay things by tens or hundreds of milliseconds because then telemetry will back up on our customers' servers. So once I decided to test out Shepherd, how much effort was it to actually move Shepherd over? Well, we needed to do three things. First of all, we needed to migrate our base images and tooling. In this case, we were using Amazon Machine Images, but the same process would generally hold for moving Docker containers as well. Secondly, we had to do an audit of our application code for architecture-specific libraries and dependencies. For instance, things containing inline X86 assembly. And then third, we had to change our continuous integration and delivery tooling to produce the right architecture-specific build artifacts. The reason for this is that we are a service that uses Go. So we natively compile our binaries. However, those binaries are generated from architecture-independent source. So let's take a quick look at what that looks like. So in terms of the base images, what we had to do was we had to make sure that all of our dependencies, such as the OS query security auditing system, every dependency such as the Honeytail integration that writes log files into Honeycomb, things like making sure that we are installing the right version of the Go runtime libraries, as well as things like, hey, are we using all of the correct OpenTelemetry binaries? Do we have the correct marker deployment libraries for indicating system events? And do we have the right telegraph binary for writing metrics? Those are some of the key things that we needed to make sure that we had ported over. Additionally, we had to make sure that Chef was running successfully on a version that was supported, because that would make sure that our Chef recipes would mostly work right out of the box and be able to be used to generate both AMIs as well as to generate our actual, as well as to run continuously to keep our architecture converged correctly. So we wound up having to do a few changes, for instance, just to say, hey, by the way, the source AMI for our Packer images needs to be adjustable. The instance type needs to be adjustable. And we need to build both a ARM64 and an AMD64 AMI. Once we did those changes and made sure that Chef was able to run successfully in both environments, we were off to the races. And as I mentioned, we have agents, right, such as Honeytail, which parses log files. So we just needed to make sure that we were building it both for ARM64 and AMD64. And once we did that, again, anyone, both Honeycomb and non-Honeycomb environments, could use our Honeycomb agent. So we had now a Packer image that was running Chef, that was building an AMI. But then we had to think about migrating, making sure the OS query was compiled correctly, and then compiling our own binaries. So we changed our continuous integration system to take the Go architecture as a parameter and to export it so that the Go binary that was building our artifacts could successfully know which architecture am I building for. And then we would just parameterize it. We would say, build one set of ARM64 binaries and build one set of AMD64 binaries and write each into our artifact repository. And then from there, we had to make our continuous delivery system know that if you were running on ARM64, this is where the artifact and checksum lived, and then fetch the appropriate artifact. So once we'd done that, at that point, we had the Shepherd service running on one test instance, and we started having it serve traffic. So we didn't need to have our CI system natively run on ARM because Go supports cross-compiling out of the box. As it turns out, building ARM Docker images is a little bit more problematic because it has to be slow in order to use QEMU in order to build those Docker images. But that wasn't a problem that we had at the time, and therefore we were able to just build a Go ARM64 binary. As Arthur said, if you're using Java or Python or Ruby, those are architecture independent. You don't need to make any changes. You can just download the appropriate runtime for your architecture and you're fine. If you had C++ or hand assembly, I'm sorry, that's going to be a lot of work, right? It's doable, it just takes a little bit more time. Whereas for us, it was just a matter of tweaking that single environment variable, GoArch, and then a lot of glue in order to make all of this stuff wired up successfully to our internal systems. So once we did this, we were able to deploy on M6G a few Shepherd instances and verify that we were getting a lower cost comparing on-demand to on-demand, that the median latency went down by about 10%, and more importantly, the tail latency, the 99th percentile of requests, dropped significantly, almost by a factor of half. And how long did this take? Well, it took a lot of wall time, I would say, but it didn't take that much of my active working time. It was a few spare afternoons. And, yes, I'm an experienced systems engineer, but the results of me tinkering with this stuff and making all of the improvements to all of the underlying systems, such as OS Query, meant that anyone can now benefit from this out of the box. So we did A/B testing next. Once we had a few instances running, we used the same build ID with different compilation targets on a single service, and we started routing traffic to those and differentially comparing the results. And eventually we were running 20% of our traffic to dog food on M6G. And you can see that this is a log scale, by the way, but you can see that the distribution of latency shifted dramatically to the left, right? You can see that the shoulder of the curve is right here, whereas the shoulder of the curve has shifted over by half of an order of magnitude, right? That's really, really significant. Additionally, we are able to look and see that the P50 is very load invariant, right? That when you had a lack of full saturation, right? When you're running the same number of queries per instance going against M6G versus C5, you can see that the P50 was rock solid at 5.5 milliseconds no matter what. Whereas the heavier loaded C5 and C5N instances that were running at 50 to 60% CPU saturation, that the more traffic they got, the slower they would get. So you could see here that, the CPU was far from clipping, so we knew that we could hit it a lot harder, right? So the Graviton2 instances, we were able to really, really focus in, right? So the M6G instances were running at most 60%. The C5 instances were running at 85%, and they were running very, very painfully slow. So we decided we were going to go ahead and just cut everything over, right? Like, so for a period of about a month, we ran an experiment running 100% on Graviton2. And we found that we were able to run about, 30% fewer instances during that time window. But all good things have to come to an end. The Graviton2 limited availability window closed for a little while while the team was getting in shape to launch Graviton2 to the full world. So we wound up switching back over in August once there was both C6G and M6G availability. And that really let us hone in on running Graviton2 in production for the entire Shepherd workload. And not just for dog food, but for production as well. So this is the kind of cost savings that we saw when we migrated the dog food workload over for real. We saw that the cost, basically halved, right? That we saw slightly more than 40% cost savings when we moved from C5 to C6G instances. And we eventually threw in M6G instances as well, just to benefit from increased diversity of instance types for running on Spot. But really, C6G is kind of our lowest cost preferred instance for running the Shepherd workload. So what happened next after we successfully ran Shepherd? Well, it turns out once you migrate dog food Shepherd, you can then migrate prod Shepherd and see, the same cost savings. A little bit more usage of M6G on Spot because we run more and more instances. So we needed to have a little bit more Spot diversity, right? So very, very compelling, very, very compelling cost savings from running on Graviton2. We decided then, what about migrating Retriever? Right, Retriever is a stateful service, and we discovered that M6GD was available, right, in about October of last year. So when M6GD was available, that meant that we could finally get that local NVMe storage. And the thing about Retriever is that it requires only a modest amount of SSD, and therefore we've been running it on i3 instances, which are the high SSD capacity Intel instances of the previous generation. i3EN is the newer generation, but it offered way more SSD than we needed. So as a result, what was happening was the Retriever instances were previously really, really pegged on CPU. And we looked and we compared i3 instances, i3x large instances, to C6GD instances. Or sorry, to I think M6GD instances. So we discovered that we could run M6GD 2x large instances for only 10% more than i3 x large instances. And this would enable us to scale out the capability to index more data and to run more queries at basically the same cost to our users. That for only 10% more cost, we could get twice as many cores, and each core would perform 50% better, right? Like that is a win-win-win. So when we swapped over, we very quickly discovered that the P99 of the amount of time that it took to analyze any one particular segment of data, it dropped precipitously, right? It dropped by a factor of 50%. right? That the P99 used to be that, to analyze a single segment file would take between 500 milliseconds and 1500 milliseconds. And after we swapped over, the P99 consistently stayed below 500 milliseconds. That's pretty cool, right? So we wound up very quickly migrating that over to production. So in late August, we moved all of production retriever over to Graviton2, to the M6G type. And you can see here that the amount of traffic that those retrievers served tripled over the course of the year 2020, right? That from August of 2020 until March of 2021, traffic went from about 4 million total spans per time period to almost 9 million, right? And you can see that the latency stayed basically the same as prior to us switching over, that we were able to serve 3 times the traffic at only 10% greater cost. I think that's a pretty big miracle. So there are a couple of road bumps, right? Like for instance, when we did the initial migration, we were trying to provision M6GD right out of the gate, right as soon as M6GD launched. And there were not enough M6GD instances available in in one of the US East availability zones. So I talked to the AWS team, and they were super keen on getting us to have a good experience. So they rearranged some instances and provisioned more in US East 1D for us, and everything went well. We finally were able to migrate all of our retriever storage. And then finally, one of the last pieces that we went after was the Kafka path, the kind of last piece in that data storage flow of having that storage piece between our ingest workers and our indexing workers. So we've been using Confluent Kafka for a very long time, but on i3 Intel instances. So we decided that we wanted to leverage Confluent's tiered storage in order to use less local SSD to no longer be constrained by SSD, and to kind of right-size things in order to be located on C6GN instances and using the newer AWS Nitro on the C6GN instances. So we changed multiple variables at once, right? Like we adopted tiered storage, we changed from X86 to ARM, we changed instance types and shapes, and we also had a newer hypervisor. So those 3 or 4 things changing all at once was a little bit more bumpy than we would have liked, because we ran into a few things that no one had encountered before. For instance, we discovered that you really need to be using the Corretto JVM distribution, or else you're going to have operations that took a very short amount of time on x86 instead spend time thrashing in the kernel, because the default OpenJDK distribution didn't support using the ARM64 intrinsics. So things like that were things that we ran into. But the thing that finally was a problem for us was that we were seeing some weird behavior with network throttling that we couldn't get to the bottom of, and it wound up causing us a lot of operational pain. So we wound up saying, okay, like we're going to revert that change for now. We're open to C6GN in the future, but that we really needed to stabilize the operations of all of our services first and foremost. That we'd hit the point where cost savings was no longer our highest priority, and instead we needed to spend a little bit more time working on reliability, keeping in mind what I said earlier about kind of service level objectives are a room for experimentation. When you deplete your room for experimentation, it's okay to spend more money to preserve reliability. So today, the services that are fully on Graviton2 are Shepherd, the ingest workers, Retriever, the indexing workers, Poodle, which is the web tier front end, which actually, I mentioned before, right? Like I said, it was a tiny service we, not worth doing the initial experiment with. Once we validated that we could just run it on ARM64, we just ran it actually on A1 Graviton1 instances for a while before we moved to Graviton2, because those are GA. It was a no-brainer. It was pretty simple to do. And then finally, we've moved over Refinery, which is our tail sampling service that enables us to not have dog food be the size of production in order to get all the telemetry out of production. So the Refinery service we built for ARM64, our customers are using on ARM64. And in fact, it's our preferred configuration because the performance is great. And it really is a situation where you're better running on ARM64 out of the box than AMD64. It was really designed to run on ARM64 just fine. So those are the four key services out of our eight services that are running on Graviton2. And we validated that at least, it is possible to run the full data flows through Kafka as well. It just doesn't make sense for us right now at this moment. So Graviton2 is going really strong in Honeycomb. About 93% of our core count is running on ARM64. And in fact, if you look at what that graph looks like today, you can kind of see those key moments where we migrate each service over, right? You can see here that, we had a lot of Retriever x86 instances. We had a lot of x86 64 Kafka instances, and everything of Shepherd was there. We started doing those Shepherd experiments, and then we shut them off temporarily until Graviton2 went GA. We immediately migrated Shepherd. We immediately migrated Retriever. And then after that, we finally went and said, okay, we're shutting down a lot of those Kafka instances. We're migrating over Refinery to run on ARM64. And this is where things stand today, right? Like these three biggest services that we have are all running on ARM64. So what are the takeaways for you as someone who's contemplating running Graviton2? Have a measurable goal in mind, right? You need to be able to benchmark against baseline. You need to understand what are you measuring, and not just CPU percentage, right? But actually, what's your end user visible latency and what is your cost, right? Do your existing dashboards reflect customer impact, or are they just CPU dashboards? So start by measuring something and then learn and iterate. I actually had some complaints from people who said, oh, we weren't able to see your 30%, 40% performance increase. And I asked them, were you actually running it to breakage, right? Or were you just saying, okay, I'm seeing, the CPU went down from 30% to 20%, right? Like that doesn't tell you anything. You have to say, my target is to have query latency be 300 milliseconds at P99. I'm going to run it hotter and hotter until I no longer can meet that threshold, right? That's how you actually get that cost savings. Because if you're not aware of the performance properties of your system, for instance, that Graviton2, that cost savings comes from running it hotter and not having symmetric simultaneous multi-threading on, right? If you don't leverage the full benefits of it, you're not going to see the full benefits. So measure that thing like, user performance, run hotter until you break that promise, and then learn and iterate and figure out, okay, this is what we're standardly running at. This is the cost savings that we're actually achieving. But also make sure that it actually is worth it to you, right? Is cost your biggest factor right now? Maybe it is, maybe it isn't, right? And you have to balance cost against things like operational complexity, tech debt, maintaining two architectures at once, thinking about your upstream dependencies, thinking about your vendors, right? And this is a place where at Honeycomb, we've tried to at least get that factor out of the way for Honeycomb services, right? That if you are a Honeycomb customer, we 100% will support you on ARM64 rather than being like, what is ARM64, right? We're here to support you. We build our binaries out of the box. We have that first-hand experience of running our systems on ARM64, so we're ready to support you. But if you're not in that situation, maybe you need to pressure your vendors to do something first before you go and leap ahead of your vendors. The other important thing is to take care of your people, right? In the course of doing these experiments with Kafka, with migrating our Kafka onto Graviton2 instances with significantly less local SSD, we caused a bunch of operational breakage. And we really needed to make sure that we were taking care of our teams, right? That we were handing off between people who are working incidents. That we were encouraging people, like, you worked really late last night, go take a break, like, take the day off. Like, we got this. We got this without you, right? Like, you need to go and take some time off. And we also, said, right, like, seriously, like, if you're busy working incident, you shouldn't have to worry about cooking dinner too, right? Like, go and buy a meal on the company credit card because, we want to make sure that your stress level is managed. And optimize for safety, right? So make sure that people are thinking about, not just like pushing and running out the door, but instead, like, how do we make sure that this is sustainable, right? If it takes, 3 hours for me to write this pull request, I'm probably going to want to watch it, right? Deploy at the beginning of the day and watch it the whole day. And if I'm deploying an infrastructure change, right, like I'm not going to ship it right before I walk out the door, right? You need that tight feedback loop. You need to be watching things in production. But that means that you just have to be mindful of what is risky and what is not risky, right? A well-tested change you can ship at 4 p.m. on a Friday. A change that's a little bit more risky or that gives you a little bit of butterflies in the stomach, right? Like maybe push it earlier in the day, maybe push it on a Thursday, right? I think it's a spectrum when we talk about Friday deploys. So if you're interested in learning more about our Graviton2 journey, you can see our initial set of ARM64 validation from March 2020 at go.honey.co/ARM64. And if you're interested in seeing where we wound up a year later in April of 2021, you can see our Graviton2 1 year later retrospective. So that's what I have for you today. If you're interested in learning more about observability and how we do the magic at Honeycomb, you can read my colleague Shelby's Introduction to Observability 101. And by all means, reach out, honeycomb.io/Liz. I'm at Liz the Gray on Twitter. And a bunch of the Graviton2 team and I monitor the hashtag Graviton2 hashtag on Twitter. So go and post to that hashtag if you're having any questions, if you have any doubts. I and the team at AWS are really, really happy to see people using Graviton2. Oh, and by the way, right, like in addition to saving you money, it's better on the environment. It's just the right thing to do, right? Like cutting your carbon impact by 50%, by 100%, like that is one of the gifts you can leave to future generations. So thank you very much. And now I think Arthur and I are going to talk a little bit about what we shared.
Thanks a lot, Liz. That was an amazing presentation. So today, folks, you've been watching to an introduction to Graviton2 based instances. I've mentioned a couple workloads that you can target to do a migration and benefit from the lower cost, the better performance, and the better carbon footprint that the Graviton2 based instances are bringing. Liz is doing an amazing job. I particularly also like the way they're treating their people. That's just amazing. Thanks, people, for attending. And I hope you will appreciate your own Graviton journey. Have a nice day, folks.
Bye. Thanks for joining us.